All right, everybody, we have an asynchronous assignment reviewing linear regression. And today we will be starting out. So just a little review of the process. Start with your data. You've got two variables for every individual in a sample, and you want to investigate the relationships. So first, graph and describe. You get a scatter plot, and then describe using DUFs. Check for the correlation to kind of measure the strength of a linear relationship if it's linear. Then you can make a prediction model, but only if there is an explanatory response relationship. We've been working with the least squares regression line. There are other prediction models, but that's the one we've been focusing on. After that, we evaluate the model, checking R squared, standard deviation of the residuals S, and a residual plot to see if the model is appropriate. All right, for DUFs, just as a quick reminder, which is different than for one variable, we use SOCs, right? For DUFs, we look for direction. Is it positive or negative? Unusual features, are there outliers, influential points, gaps? Is the form linear or nonlinear? And then for strength, is it weak, moderate, or strong? So step one, let's check a graph and we'll describe it. So this is an example from project where you guys found the trip distance and round trip cost for some spring break destinations. For this graph, I would say there is a moderately strong positive linear correlation between the distance in miles of a trip and the round trip cost. There do not appear to be any outliers or unusual figures in the plot of the data. You can confirm that with the calculation of correlation. Quick reminder about what correlation is. It measures the direction and strength of the linear relationship. This is the formula. We do not, luckily, need to calculate this by hand. I would really start by measuring how far X values and Y values are from their respective means. And then I basically do a conversion and I divide by the standard deviation. I find how many standard deviations a point is from the X direction, how many standard deviations in the Y. This conversion is really useful. We're going to spend a lot of time with this coming up soon. It's called a Z-score. So these are Z-scores right here. And then I find the products, I multiply them together and basically find the average. For that example, when we calculated the correlation coefficient, luckily Staplett does this super quickly, and we get that the R is 0.847, which confirms that moderately strong positive association. Here's this slide right here to kind of remind you of kind of the continuum, right? A positive one is a perfect positive correlation, 0 is no correlation, and then -1 is a perfect negative correlation, and some other pictures in between. Some facts: correlation doesn't care which is X and Y. R is not affected by change of units. It's been standardized, so it doesn't really have any units and isn't changed if I change the units. Correlation is always between -1 and 1. It only measures linear relationship and it is not resistant. Watch out for causation. Correlation does not imply causation. It measures association. It frequently happens that two variables are highly correlated, not because one is causally related to the other, but because they're both strongly related to a third. A well-designed experiment is required to really establish causation. When we're calculating correlation, we always start with the mean of X and mean of Y. I'll come back to this because this calculation is important when considering how the influential points work and why they have such a big influence on correlation and on the mean and standard deviation. And just those Z-scores, and kind of this tells me why I get a +1 or a -1. Okay, let's look at an example right here. Here I have this data. Crisis management is the explanatory variable. Family strength is the response. This was from an experiment done. And I would say there is a positive weak association between crisis management score and family strength. And there is one possible outlier at 0 crisis management and 52 family strength. So I can see right here, this would be a high leverage point and would really affect the slope of the line and the y-intercept. It would probably decrease the slope, because if I drew a line without it, kind of be right in the middle of this data. If I drew a line with it, it would be over this direction. It would increase the y-intercept and probably increase the correlation. And notice in my answer, I've got context, direction, unusual features, and form, and the strength. Here's one more example, and here I've got there is a strong positive linear association between highway MPG and city MPG. There is a gap between 41 and 46. So again, I've got the direction, an unusual feature, that gap, the form, which is linear, and then the strength, which I said strong. Let's move on to prediction models. When I have an explanatory response relationship, I can go ahead and work on making a line. So in the spring break example, we had the explanatory variable was distance of the trip in miles, and the response variable was the round trip cost. The least squares regression model, it really minimizes those squared distances to the line. And our form of the line, it's the y hat equals a plus bx. Just remember that form so that when you see it, you're not confused about the different direction. For our prediction model here for the spring break data, my y hat equals 102.1341 plus 0.0839x. And this was from Statlet, right? A student put their data into Statlet and then calculated the least squares regression line. And I can see where I have the y-intercept is like 102 approximately, and then the slope is 0.0839. Just a quick note, oftentimes when we graph these scatter plots, we don't have it does not start at 0. You cannot get the y-intercept looking at the graph because this graph is not complete. It doesn't go all the way to 0, 0, right? It's been amended. So just be really careful of that you have to use the calculation, and you can't just look at the graph because it won't show you, because it's kind of zoomed in on just the right spot. Interpreting the slope in context, our slope was 0.0839. So this means that for every mile added to a trip, the predicted cost increases by 0.0839, or about 8 cents. The y-intercept means that when a trip's distance is 0 miles, the predicted cost would be $102.13. And this is not applicable in the situation because no trips are 0 miles. Oftentimes our y-intercept is not meaningful in context, but it's very helpful mathematically. Let's make a prediction. Denver is 947 and 88 miles from SFO. What's the predicted cost of a round trip ticket? So you replace X, substitute in the distance, 947.88 miles, and then multiply and add, and we get that predicted value is 181.66, and rounding that, the predicted cost for a round trip to Denver is about $181.66. $181.66. Let's go ahead and evaluate that model. R squared is called my coefficient of determination. It's always between 0 and 1. And 0 is weak, 1 is strong. And I have this interpretation. I'm going to go to the next slide. So we kind of had the sentence frame. I'm going to fill in the blanks. I have blank percent, R squared goes there, of the variation in the y variable is explained by the x variable. So we're going to fill this in. My R squared is 71.8 or 0.718. So that's 71.8% of the variation in cost of a round trip is explained by the distance in miles of the trip. So again, I have the percent of variation in y explained by x. Here's another one. In this example, X is the rifle sales and Y is the US public mass shootings. I'm interpreting R squared equals 0.62. I have 62% of the variation in yearly mass shootings can be explained by the linear relationship with rifle production. My residuals are kind of the Y distance, my error, and I can find them by doing the actual or the observed minus the predicted. So let's do that for Denver. For Denver, we had the calculated cost, right, of $181.66. The predicted The actual, if I looked it up on, you know, the Google Flights, was $87. So we take 87 minus this predicted and get 94.66. So the residual, this negative 94.66, that means the cost is $94 under expected, almost $100 less than expected. The standard deviation of the residuals is just the typical. So if I have small residuals, I get a small s, which is a stronger correlation and less error, right? Larger residuals, I get a weaker correlation, larger s. Okay, so standard deviation is a typical distance between data points and the mean, and standard deviation of the residuals is typical error between data points and the least squares regression line, typical residual length, that vertical distance. Let's interpret S here. So S is 60.986, and so this means that for the actual cost of round trip, this means that the actual cost for a round trip for a given distance of the trip in miles deviates from the predicted on average by $60.99. It's like about $61. Residual plots, what they do, why we do them, is they basically zoom in on my graph and kind of show curves in a more obvious way. So on the left, on the scatter plot, it's kind of hard to see this curve. It's kind of subtle. And when I have the residual plot, I have this really pronounced curve. When I see a curve pattern, I know that my linear model is not a good fit. I should be making a different, using a different prediction model, whether it's exponential or quadratic or polynomial. Another plot that's not great, another residual plot that indicates a problem with the model is if I get this heteroscedastic effect. And that's basically when as the X values increase, the variation increases. So like here, I've got kind of X, it gets bigger and bigger and bigger. I get this spray pattern. That means my model is not working great. Let's look at the residual plot from that example we've been talking about of trip distance, and then the cost. And the residuals here show pretty good scatter. And so there does not appear to be a trend in their placement. This demonstrates that the linear model of the least squares regression line fits the scatter plot for the data. And it's excellent. This response really expresses that I'm not looking at the actual data, right? I'm looking at the residuals and I'm using it to evaluate the line on my scatter plot. Some additional topics, computer output. You definitely want to familiarize yourself and make sure you're comfortable writing a line that here this constant, that's my y-intercept, and the slope comes right below it, and that's really the coefficient in front of the x variable. So here income is x, this 0.001 is the slope. So my line is negative 14.7 plus 0.001x. There's two more numbers you need on here, standard s and r squared. The rest of the stuff you don't need now. So let's practice writing an equation. Here is my output. I've got, and my line, I'm going to use these first two right here. So X is my amount of detergent. I get that from my x-intercept label. Y is the height, and these were data from bubbles, height in millimeters, so bubble height in meters. And then my equation is negative 2.679 plus 9.5x. I'm going to interpret the slope, that 9.5. The predicted bubble height, that's my y hat, will increase 9.5 millimeters for each gram of detergent. Let's look at S and interpret S. It was 1.99821. The bubble height predictions are likely to be off by an average of 2 millimeters. Let's identify R. So R squared is this 96.9%. So 97% of the variation in bubble height can be explained by the amount of detergent. And I rounded because it made more sense to me. Let's talk for a minute about extrapolation. Extrapolation, so here is data about year and the percent of the US population that is overweight. So notice I've got this solid linear trend. Probably correlation is really, really close to 1. Kind of moves around a little bit, but it's steadily increasing all the way till the data stops here at 2004. And if I was going to project this, notice the bottom one really takes this off. I would see that if I keep going out at the year 2048, I would hit 100% of the population overweight. And does this really make sense? And the answer is no, right? And extrapolation is dangerous because this trend may not continue. It's like, sure, if we keep going at this rate, it's eventually going to get up here to 100. But do we really think it's going to be likely that every single person in the United States will become overweight? Probably not. Very, very unlikely. And so what would make more sense is if that was, if this was, I had some sort of logarithmic model. And so I want to be careful extrapolating because trends don't always continue. I want to talk for a second about the difference between outliers and influential point. So this one on the top, this point way up here to the right, is not an outlier because it's really close to the line. So if I have something that follows the general pattern of the line, it is not an outlier. This one down here is an outlier because it's far away from the line in that Y direction. High leverage points, when I have a point that's very far removed from either direction in the X direction, is far from that X mean, it's going to have an effect. It can have an effect. Sometimes it affects the slope, sometimes not. This one, it may or may not change the slope, but it would definitely significantly increase R and R squared. And so you just want to be careful of those influential points. An outlier in the Y direction, if it's kind of solidly in the middle, close to kind of the mean of X, it might lower R, but it wouldn't have an unusual effect on the slope or Y-intercept. One more additional example, we'll go through this one quickly. If I am given data, this is about social distress, and then they measured brain activity. You all looked at this, and we saw here, if I made a scatter plot, there is a strong positive linear association between social distress and brain activity, and R was 0.75. So you're using that staplet and then describing the R just tells me a little bit more numerically that, yep, it's a strong or moderately strong relationship. Let's look, you all did an investigation on iPhone sales. We looked at year and number of units sold. First, we made the scatter plot, and it showed a strong positive linear correlation between year and iPhone sales. No unusual features. The slope, we used Staplet to get the slope. The slope right here is this 1.6050002. And so the slope, each year we expect the iPhone sales to increase by 1.6 million units. So again, I use the word expected. You could use average or predicted. The Y-intercept is -3,222 sales. And so the predicted sales in year 0 is -3,222 million units. And it's obviously not meaningful for multiple reasons. I use this model to make a prediction for the 2019 sales. I plug in 2019 and I get out 17.86. So approximately, the prediction is approximately 17.86 million units. If I then find out that the actual is 25 million units, if I subtract, I get this difference of 7.14. So the actual sales was 7.14 million units more than expected. If I look at the S, the standard deviation, it's 1.44. We can expect our predictions to be off by about 1.443 million units. To kind of finish up, I want to say, okay, so the residuals, if I can make a statement, I kind of start seeing this clear curve. And really that means that this is not the best model for my data. If I think back to why that is also, and you think about how far that prediction was when we went off, even not that far, we extrapolated a little bit and I got this, this kind of curve. So it should not be linear. All right, everybody. Thanks for listening. Hopefully this was helpful, and good luck studying for your final.